Hello, this is the section 4.8 lesson. In this section we're going to introduce confidence intervals for differences. In section 4.5 and 4.6 we introduced confidence interval estimates of a single population proportion and a single population mean. What we're going to be doing here in this section is very similar to what we've done before, except that instead of dealing with a single population, we're going to be dealing with two different populations, and we're trying to estimate the difference between those two population means or those two population proportions. The basic idea in this section is very similar to what we've done before. We're going to start off by collecting sample data, and then we'll select an appropriate critical value, and then calculate a margin of error, and then calculate a confidence interval, which is going to be a range of possible values for what it is we're trying to estimate. The biggest difference is that in this section we're going to be estimating the difference between two population means or proportions as opposed to just the value of a single population mean or proportion. In this short lesson we're going to focus on really understanding the basic idea of what we're doing and the basics of the calculations. We won't get into the theory at all. So our first example is going to illustrate the need to estimate a single the difference between two population proportions. So consider a scenario of a statistics professor who is trying to compare two online homework systems. And so she lets 95 students use the first system, and out of those 95 students, 87 pass the class. And so that means we have about 91.6% of the students in this sample pass the class. Then she lets 82 students use the second system. 62 of them pass the class, and so that means about 75% of students who use the second system pass the class. And so based off of this result, it looks like System 1 does a little bit better than System 2 in terms of the percentage of students who pass the class. But we want to ask the question, is just how much better is the first system than the second system? The first appears to be better, but just how much better is it? Okay. And so let's make a couple of observations here. First of all, we are comparing two independent populations. We're really interested in all students using the first system and all students using the second system. Not just the few students in our two samples who use those systems. We're interested in all students. So we have two populations that we're interested in. And they're independent in the sense that what happens to one population has no effect on what happens to another population. Okay. Now, within those two populations, we're interested in two population proportions. So let P1 be the proportion of all students using the first system who pass, and then P2 be the proportion of all students using the second system who pass. Now, in these two definitions, we stress the word all because we're interested in all students who use the first system and all students who use the second system, and not just the few students in our two samples. Okay. Specifically, what we want to do here is estimate the difference between these two population proportions, P1 minus P2. If this difference is positive, then it would indicate that this first system is indeed better than the second system. If this difference were negative, then it would indicate the opposite. So we're going to estimate this difference with what we call a two-proportion z-interval. Called a two-proportion because we are comparing two different population proportions. Called a z-interval because our test statistic is going to be a z-value. And so first of all, let's let N1 and N2 be our two sample sizes that come from our two independent populations. And then P hat 1 and P hat 2 be the corresponding sample proportions. Our margin of error is given by this rather simple formula, P hat times z sub alpha divided by 2. So alpha is our significance level, which we'll typically take to be 0.05. and then p hat is given by this rather nasty looking formula right here. Okay. So then once we calculate the margin of error, we calculate our confidence interval estimate of P1 minus P2 using this formula right here. So we start off by calculating the difference between our two sample proportions. This number right here is a point estimate of our difference of P1 minus P2. So we take our point estimate, subtract the margin of error, and we take our point estimate and add the margin of error, and we're all done. So requirements for calculating this type of interval are, first, both samples are random and independent. Now requirement of randomness is always necessary. And independent here again means that what happens to one sample has no effect on any other on the other sample. Our second requirement is that both samples contain at least 5 successes and 5 failures each. This is necessary so that our underlying population proportions, underlying random variables representing the sample proportions are normally distributed, at least approximately. And so going back to our example, we were given here that p hat 1 was 0.916 and p hat 2 was 0.756. N1 is 95, N2 is 82. And so now we're ready to start plugging stuff in. First we calculate p hat, and here's our p hat 1, p hat 2, N1, N2, do the arithmetic, and there's p hat. Next, for our margin of error, we'll choose our critical value. No confidence level was given in this problem, so we'll use a 95% confidence level. And so our critical value is z sub 0.05 divided by 2, which is 1.96. And then to calculate our margin of error, we'll take p hat times the critical value, and we get 0.104. And so then we plug those into the formula for the confidence interval. Here's p1 hat minus p2 hat minus e. Do the same thing over here, except we add e, and we get our upper and lower confidence interval limits. Now we would interpret this confidence interval in the same basic way as we interpreted confidence intervals in previous sections. We would say that we are 95% confident that the difference between the two population proportions is somewhere between 0.056 and 0.264. Now the 95% confidence level here means the same thing as it did in previous sections. It means that if we were to construct a whole bunch of different confidence intervals using data from a whole bunch of different samples, then about 95% of those confidence intervals would contain the true difference of the population proportions. Now, what this means in maybe less technical terms is that the first system does between about 6 and 26 percentage points better than does the second system. And so that indicates that the first system really is better than the second system, and so our original suspicion was confirmed by this confidence interval. Now, to illustrate the need to estimate the difference between two population means, consider this scenario. We want to compare two diets, A and B. And suppose we put 10 subjects on diet A and another 10 subjects on diet B, and we recorded their weight loss at the end of the trial. And so suppose that on diet A, the mean weight loss was 4.5 pounds with the standard deviation of 6.5. And on diet B, the mean weight loss was 3.2 pounds with a standard deviation of 4.5 pounds. So based off of this observation here, specifically if we compare these two sample means, it looks like diet A does better than diet B in terms of mean weight loss. Okay? So the question that we want to try to answer is just how much better is diet A than diet B, or is there really even that much difference between the two diets? Okay? And more specifically, we want to try to estimate the difference between the mean weight losses on the two diets. And so let's make a couple of observations here. Very similar to the first example, we are comparing two independent populations. We're interested in all people on diet A and then all people on diet B. And within those two populations, we have two population means. Mu1, the mean weight loss of all people on diet A, and then mu2 is the mean weight loss of all people on diet B. And like in the previous example, we stress these words all here because we're interested in all people on diet A and all people on diet B, not just the 10 people who took diet A and the 10 people who took diet B. Okay. And so specifically in this example, we want to estimate the difference mu1 minus mu2. If diet A really were better, then we would expect this difference to be positive. And if diet A were not as good as diet B, then the opposite would be true. In section 4.6, when we talked about estimating the value of a single population mean, we had two different types of intervals that we calculated, a z-interval and a t-interval. And when we calculate confidence interval estimates of the difference of two means, we're also going to have these two types of intervals. These are called two-sample z-intervals and two-sample t-intervals. The two-sample refers to the fact that our data come from two independent samples. One big difference between these two types of intervals is where the critical value comes from. In the z-interval, the critical value is a z-value. In a t-interval, the critical value is a t-value. We're going to use the two-sample t and z interval when either we know the population variances or both sample sizes are large. Large here meaning 30 or bigger typically. Now it's rarely the case that we know the population variances, so we're going to focus more on using the two-sample t-interval. Now there are two types of t-intervals. One in which we assume equal population variances, and the second type where we don't assume equal variances. Okay. And now both of these types of t-intervals have the same basic form. We're going to start off by calculating sample means, and then we're going to calculate a margin of error. We're going to subtract the sample means. That difference is a point estimate of the difference of the population means that we're trying to estimate. So we're going to take that point estimate, subtract the margin of error, and then add the margin of error, and that's going to give us our confidence interval. But now how that margin of error is calculated depends on the assumption we make about our population variances. If we assume equal variances, then we're going to calculate our margin of error using this formula here. Take S sub p times t sub alpha divided by 2. Now S sub p is given by this formula here, and is called the pooled standard deviation. And this is going to be like an estimate of the common population standard deviation. And then t sub alpha divided by 2 is a critical t-value with n1 plus n2 minus 2 degrees of freedom. And so we're going to multiply those quantities and then take them times the square root. And that's how we'll get our margin of error. Now, if we do not assume equal variances, then our margin of error is given by this formula here, where again we've got a critical t-value. But now this t-value has r degrees of freedom, where r is given by this rather nasty looking formula. And now when we calculate this, r is not necessarily going to come out to be a whole number, and if that's the case, then we're going to round that number down to the nearest whole number. So this will give us our degrees of freedom. We'll use that to get our critical t-value, then we'll take this times the square root, and we get our margin of error. Now requirements for either one of these types of intervals are number one, both samples are random and independent. Again, independent here means that what happens to one sample has no effect on any other. And then number two, both populations are normally distributed, or both sample sizes are greater than 30. And this requirement we've seen come up with the central limit theorem, and this requirement is here because the central limit theorem forms the foundation for this type of interval. So let's apply these formulas here to this example. And so in our problem, here are the values of our sample statistics that were given. Okay. Now, in our first calculation, we're going to assume equal population variances. And so first we'll find our critical value. It's a t-score. We'll use a 0.05 significance level. And so we're going to have 10 plus 10 minus 2, which is 18 degrees of freedom. And if we look up that critical value from our critical value table, we get 2.101. And so next we'll calculate our pooled standard deviation. And so here we have n1 minus 1 times s1 squared. And then similar for the second sample. And then here we've got, again, our 18 degrees of freedom. And we do that arithmetic and we get 5.59. Then we'll calculate our margin of error. So we'll take our pooled standard deviation times the critical value times square root of 1 divided by n1 plus 1 divided by n2. And we get this margin of error of 5.25. And then we'll put that all together to form our confidence interval. So here's the difference of our sample means, subtract the margin of error, add the margin of error, do that arithmetic, and there we get our confidence interval estimate of mu1 minus mu2. Now we interpret this in the same way as we've interpreted every other confidence interval. We would say that we are 95% confident that the difference mu1 minus mu2 is somewhere between negative 0.395 and positive 6.55, assuming equal population variances. Now this confidence level here means the same thing as every other confidence interval. If we were to do a whole bunch of different confidence intervals, then about 95% of them would contain the true value of this difference. Now, what's significant about this confidence interval is that the lower limit is negative and the upper limit is positive. So that means that this difference, mu1 minus mu2, could be positive, or it could be negative, or it could be 0. We're just not quite sure. And so what that means in terms of our original question is that diet A could be better, meaning this difference could be positive, or maybe not. Maybe diet A isn't any better than diet B, and that would be indicated by a negative value of mu1 minus mu2 or a value of 0. So in even simpler terms, this suggests that the results are inconclusive. Right? Our sample mean for diet A was indeed bigger than the sample mean for diet B, but that difference wasn't that big to give us any real strong conclusions that diet A really is better than diet B. Now, in our second confidence interval here, we're going to not assume equal variances. And so first we need to find our degrees of freedom. And so we're going to plug our values of S1 and S2 and N1 and N2 into this formula, crunch the numbers. And this is going to come out to be 16 point something. So we're going to round it down to 16. So that's our number of degrees of freedom for our critical value. So our critical value is t sub 0.05 divided by 2 with 16 degrees of freedom. And if we look up that number, we get 2.120. And so now we'll calculate our critical value. Here our margin of error. Here's our critical value. Here's S1 squared divided by N1, S2 squared divided by N2, and we get our margin of error of about 5.3. And then we'll calculate our confidence interval, same basic way. Here's the difference of our sample means, subtract the margin of error, add the margin of error, do that arithmetic, and we get this confidence interval. Now notice that this confidence interval isn't a whole lot different than what we got when we assumed equal population variances. And the interpretation of this is the exact same. We'd say we're 95% confident that the difference is between negative 4 and positive 6.6. And again, notice that this is negative and this is positive. So again, our results are kind of inconclusive. We're just not quite sure if diet A is really any better than diet B.